All right, so in this screencast, I just want to talk briefly about the Gibbs phasor rule, to derive it, to simply demystify its origin. So we've already seen it and used it in the past. We derive it in the screencast notes, and essentially just want to kind of go through that derivation here to try and demystify it, because all it really is a degree of freedom analysis for my system. Okay, and so what we'll start with is we're going to assume we have, so we're going to end up with pi phases in equilibrium with each other. Okay, and so we have a n component system with pi phases and coexistence, right? And so our ultimate result is going to be f. So the number of degrees of freedom that I have, or the number of independent intensive variables that need to be specified to fix unambiguously the thermodynamic state of my system, is n minus pi plus 2. Okay, so where this comes from, okay, is in step 1 is just thinking about the total variables that I need. The total variables needed, right? We're going to have a total variables needed, and then we're going to have our constraint equation, which comes from our isofugacity expressions. So if I have, a single phase, so just looking at a single phase composed of n components, okay, in order to pin down the state of that system, I would need to specify temperature, pressure, okay, and then I would need the composition of n minus 1 of the components in my system. So basically, I need to specify the temperature, pressure, and composition of that system. When I use mole fractions, I know that my mole fractions sum to 1. Okay, so I only need to specify the mole fraction of n minus 1 of those components, because once I've specified the mole fraction of n minus 1 of the components, the nth component is fixed, right? So only n minus 1 of those mole fractions are independent. So for a given phase, I need to specify temperature, pressure, and n minus 1 of those mole fraction compositions. So now if I have pi phases and they are all in coexistence with each other, okay, I know that the temperature and pressure of those phases are going to be the same. Okay, so these two variables needed, okay, will be the same two variables that I'll need in each of my phases. And then in each phase, I'll need to specify n minus 1 mole fracs. Okay, so in total then, the number of total variables I need are going to be 2. So temperature and pressure, because the temperature and pressure in each phase is going to be the same, plus I'm going to have pi phases and n minus 1 mole fracs in each phase that I'll need to specify. Okay. So again, I need to specify temperature and pressure, and the temperature and pressure in each phase is the same. In each phase, I need to specify n minus 1 mole fracs, because I need to pin down the composition of that phase. Only n minus 1 of the mole fracs are independent, because I know that the mole fracs have to sum to 1. Okay, cool. So the total variables I need are 2 plus pi times n minus 1. Okay, so that's step 1. Step 2 is our constraint equation. Okay, so what do I mean by our constraint equation? Well, our criteria of chemical equilibrium would tell us that the fugacity or chemical potential of each component in each phase has to be equal. Okay, so for my pi component system, or my pi phases in coexistence, I must have that, say, the fugacity of component I in phase 1 is equal to the fugacity of component I in phase 2, is equal to the fugacity of component I in phase 3, all the way up to the fugacity of component I in phase pi. Okay, so now if we were to consider, let's consider 3 phases. Okay, so let's consider 3 phases. Okay, so if I have a 3-phase system, okay, this would be fugacity of component I in phase 1, this fugacity is equal to fugacity of component I in phase 2, and that's equal to the fugacity of component I in phase 3. Okay, well, if I break this up, right, let me write fugacity of component I in phase 1 is equal to the fugacity of component I in phase 2, and the fugacity of component I in phase 1 is equal to the fugacity of component I in phase 3. And comparing all the phases, the fugacity of component I in phase 2 is equal to the fugacity of component I and phase 3. Okay. The issue with the system of 3 equations that I just wrote is that my third expression isn't independent. It's just a linear combination of the first two. And essentially to be this plus the negative of this. All right. So my third expression here is just a linear combination of the first two. It's not independent. Okay. So I end up with 2 independent equations. All right. So I have 2 independent equations. Or in general, when I have pi phases, I can write pi minus 1 independent constraint equations for each component. And so if I have n components, I end up with n times pi minus 1 constraint equations. All right? Because I'll have such an isofugacity relationship for each component in that mixture. And so if I have n phases, then I have n times pi minus 1 constraint equations. Okay? And so here we're assuming that it's possible for each component to be present in each phase. Okay? There are exceptions to that rule that I've come across, but extremely rare and not likely you would see such a thing. Okay? So then our Gibbs phase rule then, so the number of variables that I need to specify, f, okay, this is a big F, my degrees of freedom, is just, well, the total number of variables needed minus my constraint equations. So now I just factor and collect terms. So I have 2 plus n pi minus pi minus n pi plus n. So I'll cancel the n pi's, and I'm left with f is equal to, okay, n minus pi plus 2. Right, the Gibbs phase rule as we've seen it before. So all it is a degree of freedom balance where I write down the total number of variables that I need to describe each phase. So temperature and pressure, which is common in all pi phases, plus I need n minus 1 mole fracs to specify the composition of each of those phases. So that gives me 2 plus pi times n minus 1 variables needed to specify those systems, those phases. But then I have constraint equations in the form of my isofugacity expressions. So for each component, I can write down isofugacity expression, and that the fugacity of each component in each phase must be equal. So that gives me pi minus 1 constraint equations for each species. When I have n species, that gives me n times pi minus 1 constraints. So the degree of freedoms then is just the total number of variables needed minus my constraints. Okay, that's the Gibbs phase rule.